I will first give an introduction of the background of style transfer and our motivation to create a novel algorithm. Secondly, the contribution of our algorithm will be illustrated. Finally, a demonstration of style transfer will be given. Then we will evaluate our result. The basic idea of style transfer is simple. Given a pair of images, one is the content image and the other is the style image, and the algorithm generates an output that keeps the structural information in the content image and texture or style information in the style image. Although the state-of-the-art algorithms can learn the texture from the style image, they ignore the blank leaving information in the style image. For example, in this figure, the left artwork is depicted in detail while the right artwork left some region blank. In this example, the voidness of right artwork is higher than the left one. In state-of-the-art algorithms, the model cannot learn this information appropriately and apply it to the content image. For instance, in this example, a portrait is transferred by a blank leaving style. The foreground is delineated in detail in the output image correctly, but the background is filled with detailed texture in the output image. The proposed algorithm should learn the blank leaving style and fill the background with blank texture as our motivation. Therefore, our goal is to build a style attention void-where style transfer algorithm, which can learn from the style attention map to get the void information. Our main contributions are a novel attention algorithm with specific mathematical meaning and a novel style transfer module guided by the attention information to learn the void information from the style image. Here is the overall structure of the proposed transfer module. The content and style images are fed into the VGG network, and the feature maps of fourth and fifth ReLU layers are extracted. Secondly, each feature map is fed into the self-attention module to generate the attention maps. The attention map is used to get the style transfer module to learn the void information. The attention maps and feature maps are fed into the style transfer module. There are two style transfer modules corresponds to different layers of the VGG network. And the transferred feature of different layers is generated. They are combined at the final feature map and passed to the VGG decoder to generate the output image. To train the self-attention module, we extract the feature map. We use restructuring model to generate a residue O which is element-wise multiplied with the original feature map and add the original feature map. So the reconstruction result is then decoded to the original image. This network is trained to minimize the distance between the original image and the restructured image. According to the previous work, the important features are learned by the residual feature map O. So restructuring model is important in this project. It is used in both attention module and style transfer module. The idea of the restructuring model can be understood by the Lego interlocking plastic bricks. When we play with the bricks, we first extract the bricks from the bag and then assemble them to different parts of the Arrowman, and finally, we get the whole Arrowman. Similarly, in the restructuring model, we treat the original image Y as the bag of bricks. After transformation, the 3D tensor is flattened into a 2D matrix H. Each column represents an image patch in the original image. This step is similar to extract bricks from the bag. After that, the 2D matrix H is multiplied with the correlation matrix. The correlation matrix represents the similarity between each patch in the image X and image Y. Each column in the correlation matrix is normalized by a softmax function. So as you can see in the last equation, each column vector of the correlation matrix sums to 1. We can express this matrix multiplication as a linear combination. Each patch of output image can be represented as a linear combination of all patches of the input image. So MI is the F patch in the output image, and HJ is the Jth patch in the input image. Since the weight actually is the correlation column vector, it sums to 1, which means this is also a weighted average. So the correlation IJ also represents the relative frequency of the input patch J that is used to restructure the F patch in the output. So the matrix multiplication can be understood as a procedure to assemble the bricks. In the self-attention module, we set X and Y to be the same feature map. The final output is a restructured feature map using the image itself. So in the style transfer module, we set X to be the content image and Y to be the style image. That means you use the patches from the style image to reconstruct the image in the content image that achieves the functionality of style swap. So in the attention module, we only use the restructured feature map in the training stage in our algorithm. The attention map has a shape of hx times wx, as you can see here. It can be flattened to a 1 times nx vector, as you can see here. Original approach used the channel direction average of restructured feature map as the attention. So although the residue O contains attentional information, as mentioned, the mathematical meaning is an average of features instead of some statistic value. So that means if two images with the same blank leaving level and different color may have different results. Our approach uses the row direction average of the correlation matrix as the attention map. Since the correlation IG represents the relative frequency of input patch J, that is used to construct output patch I. The average along the row direction represents the frequency that patch J is used to construct the whole output residue. After getting the hx times wx attention map, we use k-means with 2 clusters to generate binary attention mask. There are 2 regions in this mask. One represents the void region and the other represents the non-void region. Our next contribution is to use attention mask to get the style transfer module. Original approach directly used the correlation matrix to transfer the style features. However, our algorithm will generate a correlation mask, which will be multiplied with the original correlation mask and normalized to a masked correlation. So actually, this algorithm can restrict the domain of linear combination. You can see here, as shown in this example, the content and style images are divided into 2 regions. Originally, each patch in the output image is a linear combination of all patches from the style image. But now the situation has changed. So we divide the image into different parts. The red region represents the non-void region and the blue part represents the void region. The void region means that is blank leaving. So for the red region of the content image, we take only the patches in the red region of style image to restructure the output. So for the file structure and style transfer part, let me demonstrate the result using VS Code and Jupyter Notebook. So here you can see our file structure. This codes folder include data pre-processing code and the code for style transfer. So the train attention.py, this file can be used to train the self-attention module in the first phase, and this train the style transfer module in the second phase. This one is to test the style transfer. I will demonstrate this file to show the result. the net folder contains the algorithm parts. So the models PY contains two classes. The first one is the transform class. It contains the style transfer module in different scales. And Sava test is the overall structure of our network for style transfer. Network.py contains the implementation of the VGJ decoder and encoder, and also 6 classes, including encoder, correlation module, self-attention module, and SavaNet, which is our style transfer module. Also, we have the SANet class. This is the method used in previous work. I implement here to compare it with our result. The attention net is used to train the self-attention module in the first step. The utility functions actually include some helper functions used in our algorithm. For example, do some normalization and data projection. Also, the k-means, which is really important. We use it to generate attention mask based on the attention map. Let me run the demonstration to you guys. Let me first open the Jupyter Notebook. Okay, here is our code. Let me run. So here you can see the content image and the style image. We visualize the attention map, which represents the frequency of the patch that is used to restructure the image. As you can see, the content attention sums to 1, and also the situation is the same for the style image. So we use k-means to generate attention mask. We also visualize the frequency histogram. The x-axis represents the patch and y-axis represents the relative frequency. So the output is as shown in the last image. So maybe you can try different combinations. For example, you can change the style and run the code again. Yeah, here is the content and the style images. You will have a different style. So let me go back to the PowerPoint. Okay, then let me show some result evaluation. This picture compares original attention map A with our algorithm B. We can find that for the first 2 images with the same amount of blank leaving and different color, the original output is different, but our algorithm is invariant of image color. For the third input, we can observe that our attention map assigns high attention value to a more precise region compared to the original algorithm. Here is a comparison of our algorithm A and SANet B. For this image, we can find that the result of the SANet tends to have the same line thickness in different scales. The candle, bolt, and the wave are depicted by similar texture. However, the texture is different for different scale in our result. For this image, we can find that the result of SANet has false matching case. The sky is depicted to a human face structure. Also, we can see many features like the human face, but our algorithm will not have this situation. To further show the impact of hard attention mask, we conduct this experiment. The normal setting A uses our proposed algorithm. The void setting B represents the output patch as a linear combination of only the red region from the style image. And the non-void setting C represents the output patch as a linear combination of style patches only from the blue region. We can find that different domain of linear combination do have different effect of blank leaving for style transfer. So that's the end of the demonstration. Thanks for watching.